Hello everyone. Let's kick things off with a thought. Why does a balloon swell up when you blow air into it, but shrinks instantly when you press it with your hands? The secret lies in the magical trio that governs gases, temperature, pressure, and volume. These three are like the three friends who can never sit quietly. If one changes, the other two are bound to react. Think of temperature as the energy meter of molecules. When you heat a gas, molecules gain more energy and zoom around faster. Pressure, on the other hand, is simply the force of these tiny bullets colliding against the container walls. And volume? That's just the space these restless particles decide to occupy. Gases have an incredible ability to expand indefinitely, filling any container you put them in. So, the gas in your soda can, your tires, or even the air around you all obey the same rule: change one friend, and the other two immediately adjust. Now, before we play with equations, we must agree on the language, the units. Temperature can be measured in Celsius, but chemists prefer Kelvin, where 0 Celsius plus 273 equals Kelvin. Why? Because gases follow neat rules only in Kelvin, not in Celsius. Pressure is a busy fellow with many faces: atmosphere, centimeters of mercury, millimeters of mercury, or torr. Remember, 1 atmosphere equals 760 millimeters of mercury. Volume is kinder to us. 1 liter equals 1000 milliliters, which is also 1000 cubic centimeters. Without correct unit conversion, our gas laws fall apart like a bad recipe. So the golden rule is always check the units before cooking up your gas equations. Let's start with Boyle's law. Imagine pushing down on a syringe without its needle. The volume of air shrinks as you increase pressure. That's Boyle's law in action. It says at constant temperature, the volume of a fixed mass of gas is inversely proportional to pressure. In plain words, more pressure means less space. Mathematically, pressure multiplied by volume equals a constant. So if you double the pressure, the volume halves. The graph of pressure against volume looks like a graceful hyperbola. Experiments confirm it. At 2 atmospheres, the gas takes 500 milliliters. At 1 atmosphere, it doubles to 1000 milliliters. And at 4 atmospheres, it shrinks to 250 milliliters. Isn't that like squeezing a sponge tighter and tighter? Now let's warm things up with Charles' law. Think of a hot air balloon rising majestically. As the air inside is heated, its volume expands and the balloon lifts off. Charles' law states at constant pressure, the volume of a fixed gas is directly proportional to its absolute temperature. The formula is simple: volume divided by temperature is constant, but don't forget temperature must be in Kelvin. The graph is a neat straight line passing through the origin. Let's see numbers. At 400 Kelvin, the volume is 200 milliliters. Heat it to 600 Kelvin and it becomes 300 milliliters. Cool it down to 200 Kelvin and the volume shrinks to 100 milliliters. If we stretch this line back, it predicts volume becomes zero at minus 273 Celsius, the famous absolute zero. That's the ultimate freeze. Now comes the real fun: applying the laws. The trick is simple. First, identify what stays constant. If temperature is fixed, shout Boyle's law. If pressure is fixed, call Charles's law. Next, choose the correct formula. For Boyle's, pressure 1 times volume 1 equals pressure 2 times volume 2. For Charles, volume 1 over temperature 1 equals volume 2 over temperature 2. Then, convert everything into SI units: Celsius into Kelvin, milliliters into liters if required, and only then substitute. Rearranging equations carefully gives us the unknown variable. Trust me, the most common exam trap is students plugging Celsius into Charles's law, and the poor gas ends up misbehaving on paper. Let's solve one together. A gas occupies 200 milliliters at 400 Kelvin. It is heated to 600 Kelvin while keeping pressure constant. What's the new volume? We apply Charles's law. Volume 1 divided by temperature 1 equals volume 2 divided by temperature 2. Substituting values 200 over 400 equals volume 2 over 600. Cross multiply and we get volume 2 equals 200 multiplied by 600 divided by 400. That gives us 300 milliliters, exactly as experiment shows. Isn't it satisfying when maths and reality shake hands perfectly? Finally, where do these laws matter in our daily life? Boyle's law is the hero behind syringes, bicycle pumps, and even scuba tanks, where compressing air makes it portable. Charles' law is the secret of rising balloons and expanding car tires on hot days. Together, these laws form the foundation of the ideal gas equation: pressure multiplied by volume equals nRT, where N is moles, R is the universal gas constant, and T is temperature in Kelvin. So, to wrap up, gas laws are not dusty theories in a book. They explain why balloons fly, why soda fizzes, and why engines run. Next time you sip a soft drink or watch a balloon float, smile and say, "That's Boyle and Charles at work." I hope this session made you see gases as energetic, playful particles, always ready to obey their invisible rules. Catch you in the next class with more chemistry magic.